So I'm looking at the covalent bonding question paper. These questions are taken from Pre-U. Pre-U is slightly more challenging than AS level. It's like IGCSE compared to O level. Okay, it's like um that difference, but it has been discontinued. Anyway, let's take a look. I'll give you a few minutes to do number one first, okay? A few minutes and then we'll discuss it.
What the heck is an allotrope?
Huh?
Huh? Oh
Go.
shit. Oh, sorry. Sorry, my bad, my bad.
No, 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 no. How do you not know allotrope? We learned about allotropes of carbon, like graphite, diamond, Buckminster fullerene. What do you think
Okay,
is
okay.
allotrope? How would you describe it? Same what, different what?
Same element,
Yeah?
different structure, chemical structure.
Yeah.
Oh, really?
Mm.
Oh, okay.
Um, you have not learned C, so no need to do C. Yeah. This C about energy, we haven't done this. But you can do D, um, E also. Mm, yeah, these ones you can do. Are you all doing this? Don't wait for me, okay? I'll just discuss this once you are done.
Miss Lena, where do you find this paper?
Oh, I sent it to the line.
Okay.
Miss Lina, somehow I can't like access this.
Huh? You cannot? What does it
Yeah,
say?
but I think it's my problem though. Like it says, where is it?
Miss Lena,
Yeah?
mine also like when I try to use it on my like Apple
iOS.
iCloud,
Yeah,
like
yeah.
I have to enter like the
Password.
password to the person who shared
Yeah.
something.
Okay, wait. You need to enter a password. Okay.
Yep.
Unlock PDF. Why? Mhm. Okay, can you try again? Kung Fu didn't work?
I'm checking right now.
Okay.
Miss, it works.
Okay, good.
Okay, thank you.
All right, we discussed question 1. Allotropes are substances of the same element but have different structures. Same element, different structures, okay? But you need to write the subject. What is it? You cannot just say different same element, different structure. But what has this same element is the substances, okay? And dative covalent bond is a chemical bond formed between two atoms where the shared pair of electron come only from one of the atoms. In O3, ozone, you have 3 times 6, that means 18 valence electrons, so that's 9 pairs of electron. So I'm going to draw O side by side, and I need to make sure all O's obey octet rule. So let's say this one has 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 pairs. Okay. Of course, you can also draw it like this. So if you want to show the lone pair as dots, yeah. So this is a V shape and less than 120 degree.
Miss Lina,
Yep.
okay, can you go back? Uh, this is a dative covalent bond, right?
Yes.
Where is the electron from? Like there will be one.
Oh, okay. So in terms of this, right?
Yes.
So this oxygen has 6 valence electrons. It doesn't, it needs 2 more, but so this electron pair here comes only from this oxygen. Any other question? Okay. Oh, this one is bond energy, no need. Yeah. Hydronium ion. So hydronium ion is when you have a water molecule that looks like that, and this pair of electron will be bonded to a H plus. So it's like dative, right? So you will end up with something that looks like that, right? So now there are 4 electron domains still on O, and 3 of them are covalent bonds. So the shape is trigonal, pyramidal, and yeah. So explain is you can draw for your to aid you with your explanation. So you can draw, you can say when H2O binds with H plus, the O will have 1 lone pair and 3 covalent bonds with hydrogen. So yeah, so it's trigonal pyramidal. How many lone pair? How many covalent bonds? Which molecule with 4 atoms has the same total number of electrons as the hydronium ion? electrons. So how many electrons do we have? Is it NH3 for atoms? NH3. 10 valence electron. And then O is 6, 7, 8, 9, 10, 11 minus 1. Yeah. NH3 has 10 valence electrons. Same as H3O plus. Okay. And nitrogen and oxygen are on the same period. So they must have the same total number of electrons. N has 7 plus H is 3. So 10. Yeah. Okay. Question? 9, 10, 11, 12, 8, 9, 10, 11, minus 1. Yeah, correct. A proton in H3O plus ion can form hydrogen bond with water molecule. So let's draw water again. 1, 2, 3, 4. Water. And then a proton in H3O plus. So we have to draw like that. So this O is actually the plus. 1, 2, 3, 4, 5. Yeah. So this is forming a hydrogen bonding between the lone pair on O with this one of the hydrogen. It doesn't matter which one. So we need to label the hydrogen bonding, which is this. This is hydrogen bonding. Lone pair, we label over here already. Dipole, so this is delta plus hydrogen, and O is delta minus. And bond angle, bond angle between, okay. So the bond angle is wait. Where is my pen? Okay, I don't know where my pen is. Okay, this one is 180 degree. This one is less than 109.5 degree. And this one is 104.5 degree. Yep. Question? Do you all know why I draw the plus like this on the O, not on the H? So following the same explanation as before, this every covalent bond here is a sharing of pair of electrons. So let's say this is dot, this cross, dot cross, dot cross. So the if we split each of these into 2, all right, we can like say, oh, the electron that comes from O, there are 5 electrons that comes from O. Now, O is in group 6. So if O is neutral, it should have 6 valence electrons. But if O has only 5 valence electrons, that means it must have lost 1 electron. So that's why it's a plus. Okay, That's why I put the plus there. But usually when I draw the overall structure of the ion, I draw the plus outside, because the whole thing actually adopts the plus sign, right? But here I can't draw the square bracket plus because I need to draw the hydrogen bonding. So I have to remove the square bracket. That's why I draw the plus on the O. Okay. Hydronium ion may be solvated inside this molecule. Draw the hydronium ion inside the macromolecule, showing how it is attached to the ring. So you just want to draw one because it doesn't have hydronium ions, right? Just one. So you want the H to be facing the O, because this H and these O's will form hydrogen bonding, right? So let's say this is the H, and then there is an O, and then there is another H, and remember that this is 3D structure, okay? So there is like that, and there is a lone pair at the top here. I'll just put it like that. So these will form hydrogen bonding with the lone pairs on these oxygen. Okay, again, the plus is on the oxygen of the hydronium ion. Question? When you study medicine, you will study that this is one of the ways that an active ingredient or a medicine can be transported into a certain organ or tissue in your body, is to encapsulate it inside a larger structure like this. Okay, just quickly, number 2, cesium fluoride would be, yeah, you can do this already. Dot and cross diagram, because this is ionic bonding, so it says pure ionic bonding. You have to draw something like that, and then the charge, how many positive, how many negative, okay? Use outer electron only. And why cesium fluoride closely resembles pure ionic is because cesium has large ionic radius. So that means low charge density. So low polarizing power, whereas fluoride has small ionic density, radius. So the outer shell electrons are strongly pulled towards the nucleus, right? So it's not polarizable. So not polarizable. Yeah. Therefore, like if I have to use an everyday term, cesium cannot have the power to steal the electrons from fluoride. If it cannot steal the electron from fluoride, that means it just gives the electron away to fluoride, right? Which is what ionic compounds are. Like one atom, usually the metal, gives away electron to the non-metal. Yeah. I think that's all for today. We ran out of time, but there is no Mars scheme. I thought there was a Mars scheme. Okay, so I want you to try to do some of these questions. If you have any problem, you can just let me know. Okay? See you guys. Thank you for joining.
Miss Lena,
Yes,
can you go down a bit, please?
yes.
Thank you.
Okay, go down this.
Miss Lena,
Yeah,
a question.
yeah.
When like the cesium fluoride question, this question,
Yeah.
like, do we have to explain the radius as well, or can we just say like it has a low charge density and polarizing power? Like
Oh,
just talk
use
about
use radius.
we have to
Yeah.
get the point.
Yeah.
Okay.
It's just 1 point, but we don't know what the Mars scheme wants. So we just give it all.
Okay.
Yeah.
Miss Lena,
Yes.
I have another question.
Mm.
In the homework, there was a question about the hybridizing
Yes.
wait,
Hybridization.
hybridization scheme, like, do I
Yeah.
have, for the hybridization scheme, do we have to mention the sigma and the pi bond together with the sp? Like,
No. Hybridization, you just say sp3, sp2, or sp.
okay, so like when do we have to write the sigma and pi? Like, in what?
Usually it's for MCQ question, and then you are given an organic molecule, and then you have to choose how many sigma, how many pi bonds there are.
Oh, so rarely in structure?
Yeah.
Okay, thank you.
Yeah.
Thank you, Miss Lena.
Yeah.
Bye-bye.
Bye.
Thank you.
Thank you.
Bye.
Miss Lena,
Yes.
wait, can you explain about hybridization to me again?
Hybridization.
About the ST stuff, because I still don't get it.
So we use carbon again. Wait, so you don't get how to know the hybridization, right?
Yeah.
Okay. So let's say if I have now this bond is sigma, sigma, and a double bond is composed of sigma and pi, right? Now, the pi bonds can only be formed using pure p orbital, which has this shape, the dumbbell shape, because pi bond is a result of dumbbell shape like this and sideway overlap. All right. So C has 1s2, 2s2, 2p2, but because of the nature of an atom, they always want the smallest or most stable energy state. So instead of having this kind of 2s2p, they want to just merge, right? Actually, this one is going to be excited to up here, and it becomes 1, 2, 3, and then here, right? But then you want these to be averaged out so that the maximum energy level is lower than whatever now is, right? So, but you also need one pure p orbital to form a pi bond. So one of these p orbital will not be averaged out. So you're going to just average the rest. So when you average the rest, the energy level become a little bit higher than the s orbital, but lower than the p orbital. So this one, we now have still a p orbital here, but these three are the sp2 hybridized orbital. So we have 1, 2, 3, 4. Why sp2 is because these three orbitals are composed of one s orbital and two p orbitals. So it's called sp2, right? So now what
But
it looks, yeah.
why is like one of the thing is like not average?
This one is not added because you need the pure p orbital to make pi bond in the double bond.
Is there like a case where you need like two or like
Yeah.
no?
Yes. Hang on. So here, after merging, right? S orbital looks like this before merging. P orbital looks like this. But after merging, after hybridization, they look something like this. Okay? Actually, they look something like this. So you have three of this due to the hybridization, but you also still have the original p orbital, right? So now these three things is going to form trigonal planar like that. And then this p orbital is going to go up and down the planar. All right. Yeah. So this one can form bonding with hydrogen. This form bonding with hydrogen. And then this forms bonding with oxygen hybrid orbital. And oxygen also has pure p, so that this p and this p can sideway overlap to form pi bond. So this is the pi bond, this is the sigma bond from here. Okay, so what does it mean? It means if you have C with double bond and two single bonds, and it forms a trigonal planar, this C is always sp2 because it needs one p orbital to form the pi bond for the double bond. Now, if you have CH4, these are all single bonds. So that means you don't need a pi bond. No, you don't need a p orbital, right? Because this is sigma, 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 sigma. Sigma bonds are formed from head-on overlap. So the 1s2, 2s2, 2p2, I'll just excite all the electrons like that. Okay, so these are all hybridized together, so you end up with 4 hybrid orbitals like that. 1, 2, 3, 4. So this is now called sp3 hybridized orbital because it's composed of 1 s and 3 p orbitals, right? So sp3. So all of them shaped like this. So now you have 4 like balloons that shape like that. So it forms a trigonal, no, it forms a tetrahedral. So carbon with tetrahedral structure will always have sp3 hybridization. All single bonds. But when you have triple bond, C, triple bond C, right? How many pi bonds do you have?
Two.
Yeah, you have 2 pi bonds. So you need 2 pure p orbitals. So you just hybridize these two. So it's going to be sp, 1s, 1p, sp hybridized orbital plus 2 pure p's. Okay, so the sp hybridized orbital are shaped like that again. So it's going to look something like this and something like this. Yeah, and that's why it's linear. This one is going to bond with hydrogen. This one is another carbon. This is carbon, carbon. So this makes your sigma bond. And then the 2p orbitals are going up and down like that, making 1 pi bond, and another one going forward back like that. Again, make another pi bond. So sp hybridization will always look linear.
Okay.
How about this one? N2H2. N2H2? No, N2, yeah, N2H2. What's the hybridization on N?
Do we like have to draw the
Yeah,
bonding?
I find it useful to draw first so that I know the shape and then I just go from the shape. Or the type of bond, double or single.
I don't know. Is it double?
N, so 1H, 1H. So N needs 2 more bonds. Yeah, so it's double. You have lone pair on each end.